Hello, my name is Aaron Balke, and today I'm going to be breaking down my audio classification system that uses AI and machine learning. All of the files are available on GitHub and will be linked in the description. This audio classifier was originally built for organizing drum samples for my music production company, but it is able to be expanded out and used on other audio samples as well. The actual most of the documentation I found on using these sorts of neural networks for audio classification actually came from Dr. Papia Nandi. My apologies if I'm pronouncing that incorrectly, but she provided a ton of documentation on how to classify audio samples using CNN specifically. So massive thank you to her for that. The advantages of this audio classifier are it uses a CNN model, a convolutional neural network, and the beauty of CNNs is it allows for recognition of shapes in data over spatial transformations. So for example, if you have an image and the image has a dog in the left-hand corner, and you end up comparing the network to a image of a dog with a dog in the right hand corner, for example, it'll be able to pick up those shapes and those sorts of ideas across spatial transformations. The one complication with a CNN model that Dr. Nandi's work helped out a ton with is that they're built for images in mind, and audio does not have the same sort of data that an image does. And so figuring out how to shape the audio data to fit into a RGB image data sort of box, if you will, that was the biggest complication. And what ended up happening was I just duplicated amplification data across all three color channels of an image pretty much. So the RG and B values were exactly the same in each location in this weird way of expressing it. So the Y values are the pitch values, the X-axis is time, and then the values themselves are the amplification data. So it's comparative to like a height versus width of an image, and the color values of each. Maybe a grayscale image would be the best way to describe it. As previously mentioned, the spatial transformations that make CNN models so nice are very useful when it comes to audio, because that allows for recognition regardless of pitch and time shifts. So when a kick drum, for example, is higher pitched than the ones it was trained on, it will still be able to tell it's a kick drum even if it's 6 semitones higher than most kick drums that it was trained on. Another example would be if a sample doesn't start immediately, if it takes 1 to 2 seconds to start in the time dimension, it'll be able to still pick that up if it's been trained on ones that start immediately. It allows for that shift in the shape of the data and recognizes that shape still even if it starts 1 to 2 seconds later. So those are the big advantages of using a CNN model in this situation. My data set that was used to train this model was a selection of about 2,700 of my own audio samples, and those are kick drums, snare drums, claps, open hats, hi-hats, these different drum samples. They are available here on the GitHub. I have some reserved for testing, but the samples here, they are all uncompressed wave files, and they are labeled and classified in the CSV samples metadata spreadsheet. In the repository, there are 2 Jupyter notebooks, the one that originally was used to build the model here, and then a additional one that's used to test the model and have fun with pretty much. Most of the figures used here are just examples of the different drums. We've got all of the drums organized by type, so you can see the pitch data over time of each of them. The application is available to be tested using a cloud demo here in my binder. I'll play one quickly here for you. So if you click the launch binder button, you're able to open up the space here. If you're wanting to test the demo and the model, you can go to drumprediction.ipynb. you'll need to run the first code block in order to import the model itself and all of the dependencies. It'll give a couple errors because of TensorFlow being mad, so don't worry about that though. Once that is run, you can go down here. You will have to choose in this demo one of the 5 options here for a drum to classify. Let's try the kick drum here. You will have to run the code block. You'll ask for a file path. We'll put in the kick drum. At this point, it's going to make a audio player to play it. It'll also load and turn the WAV file into a piece of data to put into the model to predict. Here's the audio player here. So we can confirm that is a kick drum based on our ears. And then this final code block takes the model and the sample we're inputting into it, makes a prediction, and then just grabs the prediction that's highest using argmax, and then it will output which one that is, and God willing it'll say kick here. Drum sample is kick. So there's an example of the model running on the cloud. You are able to test it out on the GitHub. If you are wanting to run this locally, there are dependencies listed here, and I would suggest using Jupyter Notebooks to run it as well. That way you don't have to be doing crazy things with loading the model every time and all that good stuff. And that is my audio classification system using artificial intelligence and machine learning. If you have any questions or concerns, please reach out. I'll be able to at least give some guidance. And yeah, thank you for watching.